Here we have another question from the IStructE Structural Behaviour Course. This time is about trusses, and we are trying to resolve member forces. The question is, what is the maximum force in any member in the pin-jointed truss, and is it in tension or compression? Diagonals are at 60 degrees to the horizontal chords. Give this problem a try for yourself, pause the video, and come back to it when you are done. The first thing to note for this question is that this entire structure and the loading regime is completely symmetrical. Therefore, we can resolve the vertical reactions very, very quickly. We have 1, 2, 3, 4, 5, 6, 7 vertical forces of 100 kilonewtons each. Therefore, I already know that this will be 350 kilonewtons vertical reaction each. And because it's simply supported, we have a roller support here, so that can't take any horizontal load. There's no horizontal applied load, and therefore there is no horizontal reaction force here. This is the end of our loading and reaction. Now, the maximum force in any beam or in a truss for something that's symmetrically loaded will be right in the middle. By definition, it will be in the middle. If I draw the deflected shape of this, I hope you can see that the bottom is going to tend to want to get longer, so that will be in tension, and this top chord will be in compression. That should not be a surprise to anyone. If it is a surprise, I suggest looking at some more fundamental courses than this one. But anyway, so I'm expecting tension along every single member in the bottom chord and compression in the top chord. The diagonals are a little more complicated. Okay, so we want to take a cut somewhere around the middle because we expect the maximum axial force to be there. So I'm going to take a cut right along this line here, and I'm going to look to the right. It doesn't actually matter which side, well, so it does matter what side you look at, but if you want to look at the left, you need to cut it along this line here. But we're looking to the right, just to make things easy. Okay, so then let's draw the structure out. We have 1, 2, 3, 4.5 bays at the top. We've got 1, 2, 3.5 bays, and we've got that diagonal there. Let's draw it out. One, 2, 3.5 at the top. Okay. We had 4.5 at the bottom. Okay. And I've deliberately made these kind of incomplete members because the fact is when we cut through any member, we can resolve the forces within the member. Okay, so let's draw in our applied loads. We have 3 lots of 100 kilonewtons each. And because I've already cut it just beyond the 100 kilonewtons that would have been here, we don't need to include it, but we need to include everything to the right of the structure. This was 350 kilonewtons, so already we have a vertical imbalance here. So I'm expecting, so it's 300 kilonewtons coming down, 350 going up. So already I know that this diagonal strut has to be in compression in order for that vertical load to come down. Okay, so we also know that that angle there, maybe I need to draw this bigger. Okay, that part there is 60 degrees and that one's 30 degrees. That shouldn't be a surprise either. Okay, and we already said let me just scrub that out. But okay, just remember that it's 30 degrees at the top. We already said that is going to be a compression. That is going to be a tension, and that just call that force D for diagonal. But that diagonal force is going to be a compression. Okay, so let's try and resolve. Resolve the member forces for T, C, and D, and we'll just compare the magnitudes. But I already know that it's not going to be C because it's kind of further out from the middle, so it's going to be either T or D. So we've got our vertical equilibrium we need to solve. So we have, let's see, D sine 30 degrees. No, it's not. It's D. It would help to draw this out. D is like that, and that's 30 degrees. So, sorry, D cos 30 degrees is equal to 50 kilonewtons, because we need 50 kilonewtons going down for these to balance out. So we've got D is equal to, well, cos 30 is the same as sine 60. Sine 60 is root 3 over 2. So 50 times 2 divided by root 3 is equal to 100 divided by root 3. 57.7 kilonewtons. I suspect he's going to be a lot bigger than that. Okay, and then we have, okay, we want to resolve, let's see, we want to resolve moments about somewhere. And we have to choose a point where there is some kind of lever arm, so that we can find the value of t. Because if we try to resolve a moment, let's say about here, well, that's no use because t travels right through there. So yeah, the next logical place is up here. So it's where this would have joined up, that diagonal strut. Okay, so then because this is a 60-degree equilateral triangle, all of these lengths are going to be the same as each other. They're all the same as each other, which is great because then I can then resolve these distances. So I'm going to call each one of these L. Each one of those is L, which means also that we've got this triangle. That's L over 2. That's L. So 60 degrees. So L sine 60 is that height there. L sine 60 is equal to L times root 3 divided by 2. That's going to be very necessary when we calculate our tensile load. Okay, let's take moments about up here. So we've got we need to find a place to draw this. Okay, we've got 100 kilonewtons times 1L. That's that one. Got 100 times 2L for that one. And 100 times 1, 2, 3L for that lever arm. So we had, what did we say? 1L plus 2L plus 3L. So those are clockwise moments. T will cause also a clockwise moment. So around that point, you see T will go spin it like that. So we need to add it to this side of the equation as well. So plus T times, the lever arm we just said was L times root 3 divided by 2. And the reaction force was 350, and that is 1, 2, 3, 4.5 L sine 30. Cos 60 is the same as half. So anyway, so that's 4.5 L times 350. Okay, so that is 350 kilonewtons times 4.5 L. Running out of space. Okay, and as you might expect, all the L's cancel with each other. So we're left with this equation. We're left with 100 kilonewtons times 6 plus T times root 3 over 2 is equal to 350 times 4.5, which is 1575. Okay, and so we're trying to resolve for T, so let's take 600 kilonewtons to the other side. So T divided by root 3 over 2 is equal to 1575 minus 600, so 975 kilonewtons. So then, therefore, T is equal to 975 times 2 over root 3, which is equal to, divided by root 3. 1,126 kilonewtons in tension. And that is our answer. For completeness, let's try and find the value of C, just so that we can show you that because it's slightly away from the center of the truss, it's not actually going to be larger than T. So why don't we resolve moments around this point here? Because if we resolve there, there is no lever arm to D or T, so these drop out of the equation completely. So let's resolve moments around this point here. We have, I'm going to also use black here. Okay, so we have C times the height, which we already had, was this value of h here. So that is L divided by L times root 3 divided by 2. So C times root 3 divided by 2, and we need to times that by L as well. Now that is a clockwise moment, so that also goes in the same direction as those 100 kilonewton forces. So plus 100 kilonewtons times, we've got 3 of those, so let's just sum these all up. So we've got half L for that, we've got 1.5 L for that, and we've got 2.5 L for that. So let's say L over 2 plus 3L over 2, that was 1.5, plus 5L over 2, and that was the 2.5 for that one closest to the support, is equal to, and let's resolve moments around, let's do this one, so 350 kilonewtons divided by, times 4L, times 4L times 350. Okay, and the L's will all cancel. Well, let's take the L out of the equation, but out of that bracket. So we have C times root 3 divided by 2 plus 100 times, what was that, 589 over 2. 9 over 2 is the same as 4.5, times 4.5 is equal to 4 times 350, so that's 1,400. So let's take that across. 1,400 minus 450 is equal to 950. And we've got C times root 3 over 2 So C is equal to 1900 divided by root 3 is equal to 1097 kilonewtons in compression. So as you can see, the compressive force of the top chord will be less than this tensile chord. So T is our maximum force in these truss, and it is 1126 kilonewtons. And that is our final answer. Here we have another truss structure. This one's in the form of a crane. All diagonals in the crane structure, pin jointed truss below, are at 45 degrees. What is the force in member AB, which is this one here? This one's nice. I like this question because it is something that can demonstrate some little bit of ingenuity. I've already marked it up, but these are all, if that's L, that's also L because that's 45 degrees. Now this is nice because whatever happens, because we're trying to find a member force, we have to take a free body cut. I mean, that is how you try to resolve a member force. Now with a free body cut, if you cut it, you have to look either one side like that or the other. All the force is one side or the other. Now why is that important? Well, because we've got this quite complicated loading system on the left here, including the reactions. But on the right, rather nicely, the only thing that we need to worry about is this 100 kilonewtons. So let's look to the right. And second point of ingenuity is, because the question only asks us to resolve one of the members, and unlike the previous question, we don't need to work out what the maximum forces are in like 3 different members. What we can do is just draw this. So I'm just going to just dot, and do this. I'm just going to skip out a lot of the structure because it won't matter a lot. So that total distance up to here is 8L. We've got 8 of those bays. But even that won't make a single bit of difference because we've got 100 kilonewtons going down. And because of the way we took a free body cut, that is going to be in tension. It is a crane, so tension's at the top. You get compression at the bottom, but even that doesn't make a bit of difference. We've got D for the diagonal, or force AB. But note that we haven't got vertical equilibrium yet resolved in this free body cut. So we need to find, we know that is 45 degrees. So D sine 45 degrees is equal to 100 kilonewtons. So D is equal to 141 kilonewtons. Sine 45 is 1 over root 2, so 100 times root 2 is 141 kilonewtons. And we have just solved the question. Here we have another truss. What is the maximum force in any member in this pin jointed truss? So same question as before, except wire diagonals can take no compression and all are at 45 degrees. These are all 45 degrees. Which means implicitly that these vertical and horizontal members are the same length, because if you have a 45 degree triangle, well then this that length is the same as that. Or if you just take one tan 45 tan 45 degrees is equal to 1. So yeah, that should be fairly obvious. I hope I didn't need to explain that. Okay, So let's find our reactions then. There's no horizontal applied forces, and because we have a roller on one side, that means there's no horizontal reactions anywhere. Okay, so we know that VA, let me change that to black, VA plus VB must equal to 50 plus 170 plus 90 kilonewtons. So what is that? 220 plus 90, 310 kilonewtons. Okay, so that shouldn't surprise anyone. So that's vertical equilibrium. Now, the quick way to solve this. Okay, so if in general, when you have an asymmetrically loaded concentrated force, and let's call that value F, we've got VA, VB, and that force is applied at a distance A, and that is applied at a distance B, and that entire distance is L. VA will be equal to B over L times F, that's the proportion, and VB will be equal to A over L times F. It's proportional to how close it is to the support. If you imagine if the force is being applied directly over this support, well, all the force is being transmitted down to here. So naturally, if the force is closer to a support than the other side, more force will be transmitted down to here. Okay, so what I will do then is to say, okay, so I said each one of these is L. And we have 1, 2, 3, 4, 5, 6, 7, 8. So that total length there is 8L. So what I will say is VA, as a proportion, we've got 50 kilonewtons times 1, 2, 3, 4, 5, 6. 6 over 8. What I will do is also write L on top and bottom so that you can so that it's clear where I'm getting this from, even though those L's will cancel out. Plus 170 kilonewtons times, well, it should be a half, but what I'll do is I'll write this as 4L over 8L to really enforce the fact that it is a proportion to the distance from the support. And then 90 times, that is 2L over 8L. Only a quarter of that load is going to be transmitted this side. 3/4 will be transmitted to this side. Okay, so what do we have? We've got 50 times 3/4. So that part is 37.5 plus 170 times divided by 2, 85 plus 90 divided by 4, 22.5. So VA is equal to 37.5 plus 85 plus 22.5. 145 kilonewtons. What I'll do, well, I know that VB is equal to 310 kilonewtons, which is this equation up here, minus that, but I'll also prove it in another, using the same method here, the proportion method, to show you that it's also correct. So 310 divided by 145 is, so not divided by, minus 145 is 165 kilonewtons. But if you're not convinced, let's work out VB. So let me just do those first. Okay, so VB, let's do it in the same method. We know that VB is going to take 1/4 of that 50 kilonewtons. So because it's so far away, only a small amount is carried that side. So that's 2L over 8L plus 170 4L over 8L plus 90, and that is 6L over 8L. And obviously those L's cancel, so we've got, let's work these separately. So 50 divided by 4 is 12.5 plus 170 divided by 2 is 85 plus 3/4 of 90, 67.5. And just to check, 12.5 plus 85 plus 67.5 is indeed 165 kilonewtons. Okay, so that's this rule is very, very powerful. If you've got a concentrated force that's not centered, it's directly proportional to the distances either side. Good. Okay, so that's our reaction forces is equal to, what was that, 145 kilonewtons, and VB is equal to 165 kilonewtons. Good. So we know then that the cables carry no compressive force. Okay, so how do we know which side is going to be compression and which side is going to be tension? Well, I'm going to link to my video about truss forces, qualitative truss forces, but we need to find out which side is going to, which of these is the compression and which of these is tension. If I know the bottom chord of any beam or truss will always be in tension if it's being vertically loaded downwards. So this is the tension symbol. So because we know that this is going to the left, that has to contribute something going to the right, like that. Now already we can see that this diagonal chord is in compression, because that's what happens. That's what these arrows represent. If it's pointing outwards from the center, that's a compressive force, which cannot be the case. So actually what you will find is that this is not a plausible situation, because we already know that that cannot take compression. So actually let's blot out this, or maybe not. Let's blot out that, because we know that that cannot take any force. We also know that that cannot take any force because it's a roller joint. Okay, so we've blotted that out. But if we go along the truss, you'll find that all of these are actually compression members. Our truss needs to look like this. Have I just gone too far? Yes. Like this is a truss which carries tension only in the diagonals. And just for extra proof, let's resolve this. We have compression here. And so because we've got we've got this component going up, this one has to go down and to the left. So that is our tension. And because that's going up, this one needs to go down. So that's in compression, and these are all in tension as well. And because this goes to the right, this one has to go to the left, like that. And this is true for the entire truss. So every member on the top will be compression, and at the bottom will be tension. Okay, so this is our truss system, and we expect that in a symmetrically loaded truss, the maximum force will be in the middle, but this is not symmetrically loaded. We've got 90 on the right and 50 on the left, so we expect that the maximum member force is going to be somewhere here. I expect it to be one of this, or this. Okay, so I'm going to take a free body cut right here and look to the right. So let's draw the right hand side of the structure. We need to include all the forces. For clarity, actually, I'm going to draw the members as I've deleted them, even though the truss does actually have all those extra ones, but I'm just going to draw it just for clarity like this. Okay. And we've got an applied load of 90 kilonewtons here and 165 kilonewtons here as a reaction. And we said we've got compression along the top, we've got tension in the diagonal, and we've also got tension down here. Okay, so we need to find out which of T, C, and D are going to be the maximum forces. So let's start with the easiest one first. If we take moments around that point, we can eliminate the lever arms from D and C, so we can just ignore that for the time being. And we've got our lever arm for T, which is just L. It's this length here, because that's 45 degrees, that angle. Okay, so let's resolve moments around that point. Actually, I'm just going to call that, how shall I label it? Let's just call that one X, like that point there. And we're also going to need this one here. Let's call this point Y. Okay, so resolve moments around X. We've got T times, we're doing clockwise moments first, so T times L plus, now 90 kilonewtons is also acting clockwise. Plus 90 times L, that distance there is L, is equal to 165 kilonewtons times, how many L's is that? 1, 2, 3, 3L. Okay, so all those L's will cancel. So T is equal to 165 times 3, so that is 495 minus 90 is equal to, well, should be 405 kilonewtons. Let me just check. 165 times 3 is 495, correct. Okay, good. So T is equal to 405 kilonewtons. Okay, good. Let's take moments around Y then. So T has no lever arm on Y, neither does D. So that way we can find out C. So we have C times L plus 90, yeah, that's clockwise, and let's do the clockwise first. 90 times 2L is equal to 165 kilonewtons times 4L. 1, 2, 3, 4. 4L. So those L's will cancel. So C is equal to 165 times 4. What's that going to be? It's 660, I think. 165 times 4. 660 indeed. 660 minus 180 is equal to, should be 480, yes, 480 kilonewtons. So C is a larger force than T. Okay, D, should we find D? Well, I mean, we know that that's 45 degrees. So for vertical equilibrium, we've got 165 going up and 90 going down. So D, well, sine or cos 45 needs to equal to the difference between 165 and 90. So that is 75 kilonewtons. So D is going to be 75 times root 2 is equal to 106 kilonewtons. And as we suspected, that is not the maximum force. So the answer to the question is, what's the maximum force in any member? It is 480 kilonewtons compression. And it is this member there.